And hello, we are on activity 20, just finishing up activity 19. And lesson 21 is all about probably the most famous theorem there is, the ones that students probably remember most, either from middle school or when they leave high school. It's none other than the Pythagorean Theorem. So we're going to be learning in this lesson about the Pythagorean Theorem and its converse. And so before we go any further, let's take a look at our learning targets. So we are going to use similar triangles, ding, 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 to prove the Pythagorean Theorem. So probably when you first learned about the Pythagorean Theorem, and if I asked you what is the Pythagorean Theorem, most of you would say a squared plus b squared equals c squared. Absolutely, that's probably the, if you want to call it, the formula version for the Pythagorean Theorem. In fact, the definition, the actual theorem itself, and what this is really telling us is right here. So once we prove the Pythagorean Theorem, we are going to start using it and applying it to solve problems, right? We're learning all these theorems to help us specifically find missing sides of triangles. So as we get going, if you would go ahead and draw a line right below 1b. So we're going to chunk 1a and b together. So take a minute, read through the text, complete 1a, 1b before playing through. So if you haven't done so, be sure to read what the definition of the Pythagorean Theorem really is. It says in any right triangle. So that's one of the reasons it's one of the most notable theorems there are, because we use it for any right triangle. The square of the length of the hypotenuse is, and that would be the length of the hypotenuse is c, so that square, so c squared, is equal to the sum, that's why we use the addition, of the squares of the lengths of the legs. The square of the length of the legs. So a is the length of one leg, b is the length of the other. So we'll take the square of those two lengths, add them together, and we get the length of the hypotenuse squared. So we have an example here with a kite, and our task is to use the Pythagorean Theorem to find the length of what's called the spine in a kite. Never knew it was referred to as the spine of a kite, but that's what it is, this middle section here. And so they ask you to first identify which side of the triangle is the hypotenuse and which sides are the legs. And the reason we do that is so that we properly plug in certain measurements for A, B, and C. So line XY, or line segment XY, the spine, is our hypotenuse because, and if you did not know this, it is opposite of the right angle. It's the side opposite of the right angle. Or another way to look at it is your legs, in this case XZ and ZY, those are the two sides that create the right angle. So your legs are the two sides that create the right angle. So B, what is the length of the spine? Well, now that we've properly identified the hypotenuse and the legs, we plug in the length of those legs in the hypotenuse, or define the length of the hypotenuse. So one thing about the Pythagorean Theorem, other than making sure you plug in your values properly, is that it does not matter between the two legs what you call A and what you call B. This is known as the commutative property here, such that 3 plus 2 is the same as 2 plus 3. So regardless of what you plug in for A or B, as long as you plug in the actual length of the legs, we should be able to properly find C, the length of the hypotenuse. So with that in mind, it really doesn't matter if you labeled 35 inches as A or as B. Or likewise, it doesn't matter if you labeled 12 as A or 12 as B. So when we plug it into the formula, 12 squared plus 35 squared equals C squared. Again, we're solving for C, the length of the hypotenuse. So we use exponents first. So 12 squared means 12 times 12, which is 144. 35 squared means, again, 35 times 35, which is 1,225. We add those together. We get 1,369 equals C squared. And just like we saw in activity 19, to get rid of the squared, we do the opposite. We take the square root. So we take the square root of both sides, and fortunately for us, 1,369 is a perfect square. So C is 37, therefore XY is 37 inches. Now, if you notice the connect to history, talked about several famous people, including James Garfield, one of our presidents, found different ways to prove that the Pythagorean theorem was actually true. But one way to prove the Pythagorean theorem is by using similar triangles from activity 19. If you notice, this is very, very similar to the, pun intended, to the diagram you saw in activity 19. We are going to chunk item 2. So if you would just draw a line at the bottom of the page, pause the video, attempt to write the similarity statement for these 3 similar triangles before playing through. So if you recall from activity 19, one great exercise here, especially when writing a similarity statement or trying to find which sides correspond, is to redraw the diagram separating these 3 similar triangles with this right angle in the lower left position. Because remember, these segments, now that the altitude is drawn, and now there's technically 3 triangles that we're going to look at, these segments actually act as 2 different types of segments depending on which triangle we're going to look at. So again, this is the small, the medium, the large. That is by no means an excellent way, mathematical way to describe them, but it works here. So when writing a similarity statement, don't forget you're actually using the similarity symbol, not the congruency symbol. There's no way these 3 triangles are congruent. They're similar. It really doesn't matter how you start off the first name of the first triangle, but how you write the other 2 names is very important and contingent on how you wrote the first. So I did triangle DAC using these 3 points, starting with the right angle, going to the short side, and then going to our last vertex. So triangle DAC corresponds to right angle to the short side, DC, and then B. And so we have the small, medium, and large 3 triangles that are similar to each other. And the reason we do that is so we can write corresponding parts in a proper proportion. So before we go any further, they did actually give us some letters to represent the length of each side. Instead of just saying DA, we can actually refer to DA, the length from D to A, as X. So we'll go and add those in and at the same time explain what they mean. So the length from D to A, again, we're just using some variable X to represent that length. And the hypotenuse, CA, as B, and the longer leg of the small triangle as H. And one of the reasons we do that is so we can see how parts correspond with these 3 similar triangles. Now, the one thing I do want to point out that might be a little confusing is they have told us that the length from A to B can be represented by lowercase c. Don't be thrown off by that. A lot of times in math, we name points with capital letters, if you recall from our very first lesson. And on a triangle, opposite of that vertex, we typically use the lowercase form of that point. So capital C is the right angle vertex here, and the side opposite of it, which is AB, oftentimes in math, we utilize that and call that lowercase c. So a lot of you that don't actually write all caps or that you write all caps or write all lowercase, be careful here because we do not want to mix up lowercase c and capital C. Again, capital C is a point where a right angle is formed, and lowercase c is actually the distance from A to B. So they've told us the distance from D to C, again, is H. So we see here how the long segment of the small triangle is actually the short segment of this medium triangle. Again, we said that in activity 19, these segments play 2 different roles because they're a part of 3 different similar triangles. So from D to B, we're going to actually utilize C minus X, and the reason is the distance from A to B is C. Well, we take out this chunk here, we have C take away X. So from D to B is actually C minus X. That's an X, not a Y. And from B to C, we have A. And again, this just helps us see which segments of these similar triangles correspond. And we're going to use that in item 3. Last, from C to A, we're going to use lowercase b. Again, it's opposite of vertex B, so be sure you're using lowercase here. CB, again, is lowercase a, just like we saw here. So again, the hypotenuse of the medium triangle is actually the longer leg of the largest triangle. And last but not least, C is our hypotenuse. This is also how we utilize A, B, and C back in our first exercise. So now let's press on. If you would, go ahead and draw a line under item 4. We're going to chunk 3 and 4 together. So pause the video before continuing. Okay, so the corresponding sides of similar triangles are proportional. So you can write proportions involving sides of the triangle from item 2. I have conveniently copied and pasted that diagram here. And again, we're saying that these triangles are similar, so we can write proportions. We're trying to prove that the Pythagorean theorem is a valid theorem to find the missing side of a right triangle. So let me explain how I figured out which part or which length actually completed this proportion. So I found the triangle that actually had B and X as a side, and it was here in the smallest triangle. So B is the hypotenuse of the smallest triangle, and X is the short leg of the smallest triangle. So what they did was they compared the hypotenuse to the short leg. And I'll just do SL for that. And so then in the second ratio, we see the B again in the denominator of the second ratio. So obviously they're comparing it to another triangle, again, because we write proportions of similar triangles. So I found the other triangle that contained B as a length in that triangle. And so lowercase b is a length in the large triangle. It's actually the short leg. So notice on the second ratio, lowercase b is in the denominator because we compared the hypotenuse to short leg. So we're, again, using the short leg of now the large triangle. So b was the hypotenuse of the small triangle, but it's also the short side of the largest. And so now we need to find the hypotenuse of the large triangle because we went b over x in the short. Now we need to figure out what's the hypotenuse of the large triangle and put that over b, which in this case would be c. Then doing some cross multiplication. We can't actually multiply c times x, but we can show that we want to by writing cx. And b times b, we actually can multiply those, and we represent that by b squared. When something is multiplied by itself, it's considered squared. So we have this equation, cx equals b squared. And then on the second proportion, let's talk about how to figure that one out. So again, I looked at this second ratio and saw that they were comparing C to A. So I found the triangle that was using C and A as lengths of the sides of the triangle. So C is the hypotenuse of the large triangle and A is the longer leg. So they must be comparing, in the second ratio, hypotenuse to the long leg. So in our first ratio, I need to be comparing the hypotenuse to the longer leg. That's what we mean by corresponding parts. Hypotenuse of one triangle corresponds to the hypotenuse of another in the similar triangles. So they're using A as our hypotenuse, so we need to find the triangle that actually uses A as the hypotenuse, and that's here in this medium triangle. So if we did hypotenuse to long leg, for the medium triangle, we need to do hypotenuse to long leg, which in this case would be that crazy looking expression C minus X. So when we cross multiply here, and this is just, even if you're confused about the algebra, it's important to understand what we're actually doing to solve these proportions and help those of you that kind of struggled in previous activities. So as we saw, b times b is b squared, so a times a is a squared. But when we multiply c times c minus x, we have to multiply the c times this c and the negative x. It's called distributive property. That's really what's happening here. When we multiply c times c minus x, we multiply the c by both. Now, technically, we can multiply c times c and get c squared. We can't, theoretically multiply c times x, but we can show that we want to. And so we get c times x, which is cx. So then in item 4, it says use the equation from item 3 in algebra to prove that this theorem is actually true. And I should point out that this is the same as this. These are the exact same formula, just the c squared is written on the left instead of the right. So don't get confused with that regard. So I even explained that over here in item 4. If cx does really equal b squared, then replace cx with b squared in this equation. So in this second equation, we're going to replace cx with b squared because we learned that those are equivalent values. So when we replace cx with b squared, now we want to make our formula set equal to c squared. So we will add b squared to both sides. It'll cancel on the left. And we get c squared equals a squared plus b squared, which is the Pythagorean theorem. So we have just proved this theorem. And my goodness, we are going to start using it to solve missing sides of right triangles. So our first example, we looked primarily at a kite, and now we're going to observe a rhombus-shaped kite. Now, a kite is actually a geometric shape. Now, they're referring to it as a something you fly in the air. Notice the string here. But now we're going to really observe what a rhombus looks like and some properties of the rhombus and use the Pythagorean theorem to find missing sides of our rhombus-shaped kite. So if you would draw a line at the bottom of the page. So we're going to chunk 7a and b together. So attempt 7a and b before playing through. So a couple things you might not have known, but the actual definition of a rhombus is a quadrilateral with 4 congruent sides. So very much like the square, except it doesn't necessarily have 90-degree angles at each vertex. So it's a quadrilateral with 4 congruent sides that's going to help us here. So if you think about it, if all 4 of these sides are in fact congruent, if I find one, then I can multiply that by 4 to find the perimeter. So I said find the length of one of the sides of the rhombus using the Pythagorean theorem, then multiply that by 4 because the rhombus has 4 congruent sides. Now, it is very important that you utilize these measurements properly because 28 is actually not the length of a right triangle. 28 is the length from A to C. So when using Pythagorean theorem, we have to be sure we're using lengths of sides of right triangles. And so DB, 24 inches, is actually the length from 2 vertices of the rhombus, not necessarily a side of a right triangle. So I wanted to find side AB. So if AC is 28 inches, then halfway has to be 14 inches. So the length from A to E is 14. And that's another property of the rhombus that I probably should have mentioned, that when these two lines intersect, they actually bisect each other. So AE really is congruent to EC, not just because it looks like it, but because that's one of the properties of a rhombus, is that DB bisected AC and AC bisected DB. So with that in mind, if the length from D to B is 24, then the length from E to B is 12. So these are the two numbers I actually used in the Pythagorean theorem. Again, it doesn't matter if 14 is A or 12 is B, as long as you know we're finding the hypotenuse, which has to be C. So here's my work for the Pythagorean theorem. 12 squared plus 14 squared equals C squared. We get 144 plus 196, which is 340. Take the square root of both sides. Now, I didn't mention this, but I'll be sure to clarify on your assessments later on what to round to. It's always safe to assume if it doesn't say round to the nearest tenth, that's a safe bet. But 340 was not a perfect square. That's why when you take the square root of 340, you get a decimal. So I changed the equal sign to an approximate sign because we did have to round here. So the distance from A to B is 18.4 inches, roughly. So that means the distance from B to C is also 18.4, and C to D is 18.4, and D to A is 18.4. So you could add it 4 times, but that's why you learned multiplication. So we multiplied to find the perimeter, which I called P, 18.4 times 4, and the perimeter is approximately 73.6 inches because we did have to round the edge of the rhombus. So that's one way we can learn something about the properties of a rhombus and utilize the Pythagorean theorem to find a missing side of a right triangle, then to help us find a side of a rhombus. Now, since we haven't had too many opportunities to actually apply the Pythagorean theorem, I do want to take a look at the check your understanding. These are excellent questions here, just taking what we just learned and taking it a little bit deeper. So if you would, chunk 8 and 9, you can do the work, of course, in the Mind Notes section, but pause the video, see if you can complete 8 and 9 before playing through. Okay, so if you haven't noticed, they've really been utilizing quadrilaterals in this lesson, and that's because a lot of the quadrilaterals utilize right angles. And so we could actually draw a lot of our quadrilaterals using right triangles. For example, 8, we're focusing in on the square. We just talked about the rhombus, and previously we talked about the kite. So it said use the Pythagorean theorem to show the diagonals of a square with side length s. We're trying to show that the length of the diagonals are congruent. So one of the properties of a square is that your diagonals are congruent. So what is a diagonal? It's a segment that connects opposite vertices. So we have this square drawn in red, and we have one diagonal in pink and one diagonal in green, and our task is to show that they're the same length. So to find the length of this pink segment here, one of the diagonals, I took one side, squared it, plus another side squared, and although we can't actually find an actual value here, a measurement, the length of this diagonal is s squared plus s squared, which is 2s squared. And so we're using the Pythagorean theorem here because a square has right angles, and therefore we could draw it as right triangles. So to find the length of this green segment, we're going to take this side and this side, square both sides and add it together, and we also get 2s squared. So because 2s squared is equal to 2s squared, we just show that the diagonals of a square are in fact congruent. Now a little more application work. Number 9 says, how high up a vertical wall will a 24-foot ladder reach if the foot of the ladder is placed 10 feet from the wall? So we're going to use the Pythagorean theorem here. The most important part is what lengths you plug in for A, B, or C. So I drew a little diagram here. So the ladder we have is 24 feet long, and they said they placed it 10 feet from the base of the wall. And obviously, supposed to be, the wall makes a 90-degree angle with the ground. So we are given actually our hypotenuse, which is the length of the ladder. That's why I put a C next to 24 feet. And this other distance from the foot of the ladder to the wall is either A or B, one of our legs. So I simply plugged it in for A. So 24 squared equals 10 squared plus x squared. Square both of those terms first. 24 squared is 576. 10 squared is 100. Subtract 100 from both sides, and because we're trying to solve for x, so we definitely get x squared by itself. And we get 476 equal to x squared. As we keep seeing, we're not solving for x squared, we're trying to solve for x. So our last step is to take the square root of both sides. And because 476 is not a perfect square, we get a decimal in the calculator. So we, again, will assume to round to the nearest tenth, which would be 21.8 feet. Now, hopefully that is a nice reiteration of the Pythagorean theorem. But we also took an opportunity to learn some things about our quadrilaterals, as well as prove the Pythagorean theorem using similar triangles. So as always, go back to the learning targets, reevaluate your understanding of this lesson based on those targets, and then complete the practice here below. Thank y'all for watching.